Welcome everyone. We will continue with integration by parts examples. Our first example is integral of x ln of x dx. We had a rule I, L, A, T, E. We had I for inverse, L for logarithmic, A for algebraic like x cubed, x squared, T is for trigonometric, and E is for exponentials. Now here I have an algebraic and a logarithmic, and L is before, well, this L looks really weird. L is before algebraic, so U is going to be ln of x, and du is going to be 1 over x when I differentiate both sides, 1 over x dx. dv is going to be the remaining, what do we have? X dx. Now integrate both sides. V is equal to x squared over 2. It is time to follow the arrows. Or you can just say u v v du. I don't know how you remember it. This becomes ln of x squared ln of x over 2 minus integral x squared over x will be x, so x over 2 dx. This is easy to solve now. X squared ln of x over 2 minus x squared over 2. There's also a 2, so x squared over 4 plus c. Next example, integral of ln of x dx. Again, I, L, A, T, E. I see ln of x only, so u is going to be ln of x. du is going to be 1 over x dx. dv is going to be the remaining part, which is dx itself, and v is going to be x. Time to follow the arrows again, which is x ln x minus integral of x over x, which gives us itself 1, so only dx. I don't need to write 1. And this is equal to x ln x minus x, or we can write it as x by ln of x minus 1 plus c. All right. This is a kind of unique type of integral because if you try to apply the rule I, L, A, T, E, you will see it doesn't work. If you call x cubed u or e to the x squared u, no matter what, you won't be able to solve this integral. I'm not going to do it because we already know we cannot. But what can we do is, we need to realize something. E to the x squared differentiated is 2x e to the x squared. And I have it inside of this integral. My integrand has this. So what I'm going to do is, I'm going to say u is x squared, or let's start with dv this time because dv is x e to the x squared. Well, I don't have 2. I could add it and divide this integral with it, but I'm not going to do that. Instead, I'm going to write v as integrating both sides e to the x squared divided by 2, because I want to save myself from the 2, right? So it becomes x e to the x squared. For the u, what I have is x squared, and du is going to be 2x dx. Now I can follow the arrows. X squared e to the x squared over 2 minus integral. Now let's see. V du, 2, these 2's will cancel each out. So do I have x e to the x squared dx? Again, I kind of have e to the x squared when differentiated, but there is no 2, so I will write this as x squared e to the x squared over 2 minus e to the x squared over 2 plus c. You could write it in different forms. I'm gonna leave it like this. Or maybe you can write it as x squared minus y plus c to make it look better, I guess, a little bit. For this integral, I'm gonna do the same thing. I, L, A, T, E. The rule doesn't really change. U is going to be ln of x squared plus 2 du is, do we remember how to differentiate this? You differentiate inside of it over inside of it itself, dx. For dv, we have dx, and for v, we have x when we integrate both sides. Now it's time to follow the arrows, which gives us, maybe let's continue here, x ln of x squared plus 2 minus integral of 2x squared over x squared plus 2 dx. To integrate this, I have to do a polynomial division because the degrees of the x's are the same, and I need to simplify that a little bit. So 2x squared divided by x squared plus 2, I have it 2 times 2x squared plus 4, and I don't have it anymore, so I can write this integration as x ln of x squared plus 2 minus integral 2 minus 4 over x squared plus 2 dx. Now what I want to do is, let's continue here, x ln of x squared plus 2 minus integral of 2 dx plus integral of 4 over x squared plus 2 dx. This is easy to solve, but what about this? We know that integral of 1 over, let's change the color maybe, because this is going to be a note. Or can we write it? Maybe I can clean the highlight. We know that integral of 1 over x squared plus a squared dx is equal to 1 over a arc tan of x over a plus c, of course. Now we will apply this to this integral, which gives us x ln of x squared plus 2 minus 2x plus 4. Now a is going to be square root of 2 here, 4 over square root of 2 arc tan of x over square root of 2 plus c is going to be my answer. Maybe it looks a little bit complicated. We just applied the highlight rule, and then to solve this integration, we did a little bit of polynomial division to write it in this form. And after that, we had to use this integration formula to integrate this, and then we got to our answer. Integral of secant cube x dx. This is a really nice one because this is, at first it doesn't look like you will have to do integration by parts, but actually we have to, because we can write this as integral of secant x multiplied by secant squared x dx. U is going to be secant of x because I can differentiate this really easily, secant x and x dx. If you don't remember, you can differentiate it by yourself. For dv, we have secant squared x dx. So v is going to be tan of x when we integrate both sides. Follow the arrows, we get secant x tan x minus integral of secant x tan squared x dx. Alright? I need to remind you guys one more thing. Let's write it with green again. 1 plus tan squared x is equal to secant squared x. So tan squared x is equal to secant squared x minus 1, right? We will have to use this. You will use this quite a lot, so don't forget this, alright? This is going to be secant x tan x minus integral of secant x by, now I will write this instead of tan squared x, secant squared x minus 1 dx, which is equal to secant x tan x minus integral of secant cube x dx plus integral of secant x dx. Why is this important? Because this is equal to integral of secant cubed x dx. If I call this I is going to be secant x tan x minus I, because this is the same integrand, plus integral of secant x dx, which is equal to ln absolute value of secant x plus tan x. And if I add I to both sides of this equation, I get 2I is equal to secant x tan x plus ln of secant x plus tan x, absolute value of course. And now I will have to divide both sides with 2, which gives us secant x tan x plus ln absolute value of secant x plus tan x plus c, of course. You could think like, what about if I divide it with 2? You can do anything with the plus c, it doesn't really matter, so we will leave it like this. If you don't remember the integral secant x dx, I will tell you how to solve it. I'm not going to solve it here. You will have to multiply the integrand with secant x plus tan x over secant x plus tan x. And when after doing this multiplication, you will use the substitution u is equal to secant x plus tan x, and you will figure out du, and after that you will see it will solve itself. All right? You can try it by yourself. I don't know if I solved this integral before. Of course we will if you didn't, but you can also solve it by yourself the way I just told you. Our last example in this video, ILATE. Of course, trigonometric is before the exponential, so u is going to be cosine of bx. Du is going to be negative b sine of bx dx. Now, dv is going to be e to the ax dx, integrating both sides. V is going to be e to the ax over a. Follow the arrows. E to the ax by cosine of bx over a minus integral. There's another minus, so it's going to be a plus. B sine bx e to the ax over a dx. I have to do another integration by parts, so I will do it here. Let's take this integral. It is going to be b over a. I can take it out. Of course, a and b here are real numbers. I have sine of bx e to the ax dx. Again, to this, I have to apply integration by parts. U is going to be sine b of x. Du is going to be I forgot the b, oops. B cosine b of x dx. dv is going to be e to the ax dx. So v is equal to e to the ax over a. Time to follow the arrows again. B over a sine b of x by e to the ax over a minus integral b cosine of bx times e to the ax over a dx. I want you to realize something. This integral e to the ax cosine bx dx is also inside this integral, so I'm going to call this one I, like I did with secant cube x. But before that, we need to write this back in the integral in the first equation, so, and I don't have enough space for it. So what could we do? Maybe we should just add another page to continue. Okay. And if we copy this, did I copy? No. I copy paste it here, and for this integral, now we have, I can close this, e to the ax cosine bx over a plus, instead of this I will write this now, it's going to be b sine bx e to the ax. It doesn't look good like this. Let's write it like e to the ax sine b of x over a squared. And this is of course equal to I, which is our integration here. And b sine b, okay, a squared minus b squared a squared. B squared over a squared integral. Instead of the integral, I will write I. Now, I will add this term to both sides. I plus b squared over a squared I is equal to e to the ax cosine bx over a plus b e to the ax sine of bx over a squared. This can be written as I multiplied by 1 plus b squared over a squared is equal to this this gigantic term, e to the ax cosine bx over a plus b e to the ax sine bx over a squared. I think you guys know where this is going. I will divide both sides with this term. 1 plus b squared a squared. I can write this as a squared plus b squared over a squared. So this means we will be multiplying both sides with a squared over a squared plus b squared to save ourselves from this term. I is going to be a squared e to the ax cosine b of x over a squared b squared. So a cubed plus ab squared plus a squared b e to the ax sine b of x over a to the fourth power plus a squared b squared plus c. Yeah, let me check my answer key real quick because I hope I did not make a mistake. Okay, so we don't really have a mistake here, but I just made the algebra a little bit longer than it could have been because I missed that. I can simplify the a's here and here. This would be a e to the ax cosine bx over a squared plus b squared plus, now I can simplify the a squares from numerator and denominator. B e to the ax sine bx over a squared plus b squared plus c. And this can be written as e to the ax over a squared b squared by a cosine of bx plus b sine of bx.